This video is an example of a chi-square goodness of fit test. A researcher claims that the number of cups of coffee U.S. adults drink per day are distributed as expected in the table. A random sample of 1,600 U.S. adults were asked how many cups of coffee they drink per day, and the results are shown below. At alpha equal 0.05, test the researcher's claim. So here are the categories: 0 cups, 1 cup, 2 cups, 3 cups, 4 or more. Here's the researcher's expected distribution, and here are the observed counts from the sample of 1,600. Now, the first thing to do is to set up the null and the alternative. The null statement is always some form of the statement that the distribution is as expected. Some textbooks are a little more specific. For example, I could write the proportion for the first category is 0.36. The proportion for the second category is 0.26, and so on. We have 5 categories. And the alternative is that the proportions aren't as expected, or some sort of statement of that. Okay, so there's a little bit of flexibility here. You might want to go with how your textbook is stating that. So I'm just going to put the distribution is not as expected. All right, so for this example, the null is the researcher's claim. Okay, so this is what the researcher is claiming the distribution to be. Now, I'm not going to do the test statistic by hand. I'm going to use the TI-84 to find that for me. But if you did want to do the test statistic by hand, you're going to need the expected counts. The test statistic formula is the sum in the numerator of the observed counts minus the expected. We square that difference over the expected for each category, and then we sum those all up. So the first thing to do is to get the expected counts. To do that, you want to multiply 1,600 by each proportion for each category. So this first one will be 1,600 times 0.36. The second one will be 1,600 times 0.26, and so on. Okay, now I'm going to take a little shortcut. In my calculator, in my lists, I put in the observed counts and the expected proportions for each category. So I want to create a third list by telling the calculator that I want to multiply every value in the second list by the sample size of 1,600. So I move my cursor up so that L3 is highlighted, press enter, and then down below I can tell it 1,600 times that second list. Okay, and that will quickly give my expected counts. Okay, so if you're feeling lazy or motivationally inert, this is a quick way to get those counts, especially if you need those for a homework problem or if you need to show your work by hand. All right, so I'm going to use the TI-84's goodness of fit function to actually find this. Okay, if I wanted to do this by hand, I would take each observed count minus the expected for that category and divide it by the expected. That's the first one. But then I'd have to add it to the next one, and so on, all the way down to the last category. So not that this is computationally difficult, it can just be tedious. All right, so to get the test statistic using the calculator, your calculator will need a list of counts. Okay, you can't run the goodness of fit using the observed and the expected proportion. You need the observed and the expected count. So it's another good idea to have created this third column because of that issue. To do that, I'm going to go to Stat, arrow over to Tests, and scroll down to chi-square GOF, which stands for goodness of fit. And it's going to ask for where your observed counts are and where your expected counts are. My observed counts were in list 1, and I created my third list to be the expected counts. Again, I'm not running this test using the proportions in decimal form. You'll get a crazy test statistic. The calculator needs everything in terms of counts. The degrees of freedom is the number of categories minus 1. I have 5 categories here, 0 cups through 4 or more cups. So the number of categories minus 1 would be 4. So you can change that if you need to. And then calculate. So the test statistic is 2.814. So if you had done this by hand and summed up all of those individual terms, you would get about 2.814, depending on where you round. And the corresponding p-value is 0.589. Now I know what my decision will be based on that p-value. Okay, that's going to be greater than or equal to every common level of significance, so the decision will be to fail to reject the null. But to use the critical value method, we want to find the critical value from the chi-square distribution. And this test is always an upper tail test, and the chi-square distribution is skewed right. It's a family of curves, and its exact shape, how skewed it's going to be, depends on the sample size, also the degrees of freedom. I have an upper tail of rejection, as this is always an upper tail test, 0.05 amount of area in that upper tail, and the degrees of freedom for this test is 4. Now, looking at the chi-square table that's in the current text I'm using, it reads from the critical value to positive infinity. So I want to find, and the printing is so small, very difficult to see. I want to read over to 0.05 amount of area in that right tail and down to 4 degrees of freedom. So this critical value is 9.488. And going back to my test statistic was 2.814. Okay, that's clearly in the fail to reject region. Okay, and that p-value, just to review the p-value is going to be the area further to the right. Okay, that's going to be the p-value for this test. So clearly the p-value is greater than our level of significance. So using the p-value method or the critical value method, you're going to come to the same conclusion. The conclusion is to fail to reject the null. And if we're failing to reject the null, we're in favor of the null. And the null is the claim in this problem. So there is insufficient evidence to reject the researcher's claim that the number of cups of coffee US adults drink per day are distributed as expected.